Hello, Advanced Geometry students. It's Mr. Donaldson. I'm here to talk to you today about section 9.6. So, 9.6 is going to be about allowing us to apply what we learned about right triangles and also what we learned about circles back in chapter 6. So, a couple things to remind you from chapter 6. We learned that whenever you have a circle and you have a tangent to that circle, the radius of the circle and the tangent always form a right angle. Now, why is that important? Because what we're learning now is all about right triangles. And when you can make a right angle, or when you have a right angle, you can make a right triangle. Another thing we learned is that an inscribed angle that opens up or intercepts a semicircle has to be a right angle. And to remind you why, remember an inscribed angle's measure is half the arc that it intercepts. So if I extend the sides there of that angle, I notice that there is 180 degrees of arc inside of it. It intercepts 180 degrees, which means the inscribed angle is half of that, which is 90 degrees. So keep those things in mind. Some little reminders about how you can get right angles from circles. There is another one as well, and that is this. In a circle, when you have a radius, if it bisects a chord, then it must be perpendicular to it. And the converse of that theorem is true as well. Okay, and you'll see an example of that in the first example. Let's take a look. So, in this example, it says that segment OC, which is the radius, is perpendicular to segment AB. So I'm going to mark perpendicular there. Also, it says that AB, the distance from A to B, is 24 centimeters. Now, what I just told you a second ago is that when you have a chord that is perpendicular to a radius, it must be bisected by that radius. So if that entire chord is 24, it means that AM is 12 centimeters and B is 12 centimeters. Also, we know in this problem that MC is 8. All right, I want to find the diameter of the circle. Now this is my plan. My plan is I'm going to find the radius. Once I know the radius, the diameter will be 2 times that radius. So my objective is find the radius first. Once I find the radius, I'll just double it quickly to get the diameter. Now to do that, this whole chapter, chapter 9, is about right triangles. There is not a right triangle drawn here that will help me. Now, the thing I must keep in mind is I could draw this right triangle here, but the problem is that does not involve the radius at all. So the obvious solution here is to draw the radius right here. And now check this out. I have this right triangle. Here's my radius. Let's focus on that right triangle. This is my radius. This is 12. Now, the piece of information from the given that I've yet to use is the fact that MC is equal to 8. And the way I'm going to use that is in this diagram. Remember what I told you in chapter 6? In a circle, all radii are congruent to one another. So that means if OB is R, OC is also R, which means this entire segment is R. Now, that is helpful because if OC is R and MC is 8, then OM is whatever's left over of R after you subtract away 8. So a good expression for that would be R minus 8. So I'm going to call this piece R minus 8. So now I've labeled all my sides. I'm obviously going to be able to solve for the radius, or R. So I'm going to do that right now. I'm going to set up the Pythagorean theorem by saying R minus 8 squared plus 12 squared is equal to R squared. Now remember, when you square a binomial, you have to FOIL it. You got to multiply it by itself. That's what squaring means. Plus, of course, 12 squared is 144 equals R squared. So when I FOIL this or distribute it, I get R squared minus 8R minus another 8R, which is minus 16R. And negative 8 is a positive 64. Plus 144 equals R squared. All right, now at this point, I'm going to go ahead and I'm going to combine my like terms and just kind of tighten things up slightly. And I'll get this. And 64 and 144 is what, 208? And that equals R squared. Now, you should be thinking right now, you're like, oh man, this is a bummer. This is a quadratic. I'm going to have to factor this. This is going to take a little bit of time. But if you think a little bit deeper, you'll notice that both sides of this equation has an R squared. So I'll simply subtract R squared from both sides. And I'm left with negative 16R plus 208 is equal to 0. Now I have a very simple linear equation If I add 16r to both sides, I get 208 is equal to 16r. And then I'll divide both sides by 16, and r is equal to 13. Go back and look at this problem, see if this all makes sense. I found that r was 13, and look what happens. When you plug in 13 for r, this side is 13, and 13 minus 8 is 5. Look, we have a Pythagorean triple. 5, 12, 13. All of this makes sense. So that means the radius is 13, and therefore, to answer the question, the diameter of this circle would be double the radius, so 26 centimeters. There we have it. A little bit tricky, but the goal here, you guys, is all about establishing a right triangle relationship so you can use what we learned in this unit. Let's look at another example. All right, in this case, the diameter of the circle is 50. All right, well, if the diameter is 50, that means the radius is 25. What is the length of chord AC? So what I'm going to do in this case is I'm going to call maybe each one of these little parts X. If I can find AE or EC, I'll simply double that, and I'll get the length of chord AC. And again, what I'm using to know that those parts are congruent to one another is the fact that if a radius and a chord are perpendicular, they bisect one another. So I kind of have a very similar situation here. I need to establish some sort of right triangle so that I can use Pythagorean theorem or some other thing that we've learned in this unit. So I can draw the radius wherever I want, but the obvious solution here is to draw it either from D to C or from D to A to get a right triangle. So let me just kind of type that up here. Here's the right triangle I'm going to use. Now I know the radius is 25. I know that in a circle, the radius, or all radii rather, are congruent to one another. So if DC is 25, that means BD is 25. And I already know that this part is 18, which means from E to D is 7. So what I have here is I have a right triangle, where this is 7, this is 25. And you can either set up the Pythagorean theorem to solve for x by doing x squared plus 7 squared is 25 squared. But I know my Pythagorean triples really well, so I know x is equal to 24. And again, just make sure you solve the problem. Once I set that up, I go back and look. I want the length of AC. Well, if each of these are 24, AC would have to be 48 inches. Perfecto. All right, next one. So, in this case, you guys should notice some tangents. Now remember, if we give you a diagram that looks like a line is tangent to the circle, you're allowed to assume it is. Not trying to trick you. And what, back in chapter 6, said whenever you see a tangent, the most important thing is instantaneously like, oh look, check it out. We got perpendicular lines. A tangent is always perpendicular to a radius. Alright? Now, you'll notice in this problem too that it says HA equals blank. Kind of screwed up there. I don't know what happened to my value. Let's call HA, how about 8 root 3? And again, you guys, this is given. Of course, you wouldn't like make this up on your own for a problem. You'd have that given length. I just kind of screwed up. And I'll show you in just a second, or you'll see, obviously, why having 8 root 3 is actually a nice number to start with. So, what I have here is I have a quadrilateral, ARTH. Got 120 degrees. I got some right angles. I got that the length of that tangent segment there, AH, is 8 root 3. All right? I want to find the area of the shaded part. All right, now, first thing I'm going to do is come up with a plan. My plan is to do this. I'm going to find the area of that kite, or that quadrilateral, and I'm going to subtract from it the sector. So my plan is to find the area of the quadrilateral and subtract the sector. But before I even draw my plan, I want to think about the fact that I need right triangles. So I'm going to draw this segment and cut this into 2, 30, 60, 90 triangles. Because that 120 would be bisected, giving me 60, 60, so 60, 90, and 30. So here's my plan. I'm going to find the area of both of those triangles. Now if I find the area of both of those triangles, look what I get. I get all of this stuff. But to find just the sector, I would then, or excuse me, just the shaded area, I would then subtract away this sector. And if I subtract away this sector, all that's left is that shaded region. So my plan, simply put, is I'm going to find the area of both of those 30, 60, 90 triangles. And I'm going to subtract from them that sector, which is 120 degrees. So let's see what I got. First of all, one of these triangles has a base of 8 root 3. If we take a look at it, right, I'll kind of draw how we see it. Maybe we'll look at this one here. This is 30, 60. This is 8 root 3. So that would go here in my little diagram. I got to find the height. And simply to find the height, all I got to do is apply what I know about special right triangles. If the long leg in a 30, 60, 90 triangle is 8 root 3, then the short leg must be 8. So there we go. I know that this is 8. And that's why when I gave you HA, I put it as something root 3, because it made it much easier. Now my radius is an integer. So, also, to find the area of that sector, I know that 120 degrees out of 360 is a third of the circle. So the formula here is the degree out of 360 times the area of a circle, which is pi, and the radius of that circle is 8. We just found the radius of the circle is 8. So what I have is I have two triangles. The area of a triangle is 1/2 times the base times the height minus the area of the sector. And now I just got to do a little bit of algebra. So this kind of reminds me of the last chapter where we needed to make a plan. So I kind of cut this figure out. I found I'm going to find the area of both those triangles, subtract the sector, and what's left is that shaded region. So here we go. 8 times 8 is 64. Half of that is 32. Times 2 is 64. Root 3. Before we got a little gross there. Minus 120 over 360 is a third times 64 pi. So what I end up with, 64 is not divisible by 3. I get 64 root 3 minus 64 pi over 3. And this is area. And so the area is in centimeters squared are my units. Remember, it is absolutely okay that your answer looks disgusting like that. Now, but also pay attention to the problem. It says to round your answer to the nearest tenth. So now I'm going to plug this into my calculator. So 64 times the square root of 3 minus 64 pi divided by 3 is approximately 43.8 square centimeters. So the direction says to round to the nearest tenth. You can use the pi button in your calculator and you round it. All right, real quick, we got one more quick example. All right, so you guys only have a couple minutes, so I'm going to go through this kind of quickly. So I apologize for that, but it shouldn't be too bad. So what you'll notice is we have an externally tangent segment here, or excuse me, the circles are externally tangent, and they have a common tangent segment. So with tangents, I always draw the radius to the point of tangency to get my right angles. So I'm going to do that. I'm going to do that. And in this case, this would be 4 because the radii are congruent. This would be 9. The radii are congruent. And check this out. I'm going to draw this segment, which would be 4 plus 9, which is 13. So what I'm going to do is I'm going to solve for x. So essentially, guys, my focus is on this quadrilateral. Now, we've done a problem just like this, except for without the circles, where Ms. Butler and I have given you a trapezoid, and we want you to find one of those side lines. So I'm going to take that, and I'm going to redraw it. Here's what it would look like if I drew it in a different orientation. Here are my right angles. This is x. This is 4. This is 9. And that is 13. So the first thing I would do is I would draw an auxiliary line here, do it in orange, to cut this diagram into a right triangle and a rectangle. Now, if this is 4, the top of the rectangle, then the bottom of the rectangle is 4, which leaves 5, because together those two must add to 9. By looking just at this right triangle here, I know my Pythagorean triple, I'm about to run out of time, is 12. 5, 12, 13, which means x is 12. Okay, my time is up. I hope that made sense. Ask questions in class. Have a great day.